Can a $40 mining card from 2018 run a modern RAG system with 186,000 chunks? I tested it. The corpus, documentation from 9 different tech projects. After ingestion, 186,000 chunks. The hardware, an X99 system with a Pascal mining card. This should all be e-waste. Obsolete, definitely worthless for AI. Cost? $40, at least before the Rampocalypse. Turns out it works. What you're looking at is an Nvidia P102-100, a Pascal mining card from 2018. It uses a GP102 die, the same used in the 1080 Ti. Really, this card looks a lot like a 1080 Ti 10GB that was cancelled, but it's permanently nerfed by a PCIe 1.0 by 1 bus. Theoretically, you can do things with the capacitors, but that's not what we're doing today. Like all top Pascal chips, regardless if they made it to the consumer market or not, this one can pull around 250 watts max. It was supposed to be a 5GB card, but at least some of these cards physically had 10GB VRAM, but they were firmware limited to 5. This is one of those 10GB versions. I'm going to be running inference on the retrievals from the RAG system using a 6-bit quantized version of Qwen 2.5 Instruct 7 billion. Left, default settings, 32,000 token context. My P102 is using 7.8 gigabytes of VRAM. Right, after I set the context flag to 8192, 8,192 token context, 6.4 gigabytes VRAM. That's 1.4 gigabytes less VRAM. Now, full disclosure, I caught the power reading at a weird moment on the 8K shot. It's showing 68 watts, but I think I just happened to snapshot at the tail end of the model settling into the card's memory. But that VRAM difference between 32,000 and 8,000 context, it was hard to come to terms with, but do I actually need 32,000 tokens? Not yet, at least. I set it to 8K. I saved 1.4 gigabytes VRAM. While I was doing production stuff for this video, I was able to upscale images on the P102-100 with the LLM still loaded into its memory. I didn't end up using the upscaled visuals though. Okay, context set. I ran 4 queries and recorded the time it took to retrieve information from the embedded corpus, the time it took for the LLM to inference a response using the aforementioned information, the amount of context used, and the response itself. Let's go through the results to see if this setup, which includes a decade-plus-old CPU and an 8-year-old GPU, is able to generate coherent and, more importantly, accurate information. The first query was, how do I run a Podman container in rootless mode? The retrieval took 50 milliseconds, and the LLM took 8.9 seconds to generate a response. 585 tokens of 8,192 tokens of context were used. While the response is mostly correct, it seems the LLM generated a response at a very high level, meaning it's very conceptual and it leaves a lot out, compared to what's in the corpus in the RAG system. This is because retrieval is set to pick up the 5 most relevant chunks. With k equal 5, the retrieval process is only getting the first few chunks from the corpus pertaining to rootless Podman. If you take a look at the rootless Podman tutorial available in the Podman GitHub repo, where I got the documentation from for this RAG's corpus, it's split into many separate small sections: networking, sub-UID, volumes, user config, etc. I'm using semantic chunking, so it would seem that every small section lives in its own chunk. To answer the question fully, you need chunks from all of them. The detailed parts about networking and storage live in later chunks that never get seen. I think the best thing to do to improve this particular response would be to expand retrieval to pick up 12 to 20 chunks in the future. Next query. What is the difference between a systemd service and a socket? The retrieval took 43 milliseconds. The LLM took 6.9 seconds to generate a response. 2,067 tokens of context were utilized. This response seems pretty solid. If you look at systemd's documentation, the description of what a systemd socket is pretty concise. And I wonder if this response is only so good because the actual information fit within the 5 chunks the retrieval system picks up, in contrast with what happened with the Podman response. Next query. How do you convert video to MP4 with ffmpeg? The retrieval took 50 milliseconds. The LLM took 6.6 seconds to craft the response, and 1,821 context tokens were used. None of that matters, though, because this response is mostly baloney. I'm not an expert at ffmpeg, but the query asks, how do you convert a video to MP4? This command starts with an MP4 video being converted to MP4. Then the LLM seems to offer a second command to cover for the fact that the first command was incorrect. And that one's wrong too. I've looked into how to get this sort of system to output something that approaches the correct response for a question like this, and that seems like a fun project that could be covered in its own video. Final query. Can I use CUDA with Pascal-era cards like the P102-100? Search took 51 milliseconds. Generation took 3 seconds flat, and it only needed 325 context tokens. And here's where things get interesting. There's no Nvidia documentation in the corpus, CUDA or otherwise. After the last query, where the LLM was just dead wrong, it suddenly does a complete 180. No confident BSing, just what amounts to I don't know. It couldn't find anything relevant in the context, because there's nothing in the corpus, so it admitted it. Which honestly, well, that's great. I'd rather have an LLM tell me I don't know than hallucinate some nonsense about CUDA compatibility that gets my hardware stuck in a reboot loop. So what did we learn? First, the hardware works. A $40 mining card whose underlying architecture debuted a decade ago can run a modern RAG pipeline with a 7 billion parameter model at 40 tokens per second. And the PCIe bottleneck everyone worries about? That doesn't matter, at least for single card inference. Second, retrieval depth has to match the varying semantic structures of different documents. The system D socket information lives in a larger, more continuous span of data, or it was concise enough to fit in a few chunks. 5 chunks covered it completely. The Podman rootless tutorial is different. It's split into many small sections, each its own piece. The answer to how does rootless Podman work is spread across all of them. 5 chunks isn't enough to pull everything back together. Easy fix, increase K, and test again. And finally, sometimes the LLM gets it right by adding nothing at all. That CUDA response, that's the behavior you want when there's no data. Honest ignorance beats confident hallucination every time. Next steps, fix the markdown chunker and increase K. Maybe other things, maybe trying this on other hardware configurations. Thanks for watching. More experiments coming.